Right.
So I'll start out with, are there any questions?
Oh, the test on Wednesday, it covers 4, 5, and 6, right?
Correct.
Okay.
And I do have stuff to hand back, that I meant to hand back on Friday. Apologize for that. Yep. If I don't set my alarm, I'm gonna forget again. We're done at 2 o'clock. All right. In the absence of questions, I will carry on. I believe on Friday, we did the box ramp spring problem. So I'm gonna say that I'm done with that chapter, so let's start on the next chapter. Flash back to something we did in the past. We're in box A and box B in a collision. And the fact that they exert the same magnitude of force on each other, and they touch each other for the same amount of time. So I'm gonna start out with this idea that the force on A from B, so again, force on A from B, is equal to the negative of the force on B from A. And the negative sign just indicating opposite directions.
And this is momentum?
Yes, it is. The topic is momentum. Obviously, we have not gotten there yet.
Is this chapter 9?
Chapter 8. Yeah,
Eight.
chapter 8.
I think it's 8.
I think so.
Previous chapter plus 1. Since they touch each other for the same amount of time, we're going to multiply both sides by time. And I will alternate back and forth between t and delta t. In other words, I'm just going to assume that we're starting time at the beginning of the problem, and so therefore time and final time are the same thing. From Newton's second law, what is force equal?
Mass times acceleration.
And that would be total force. So I have mass of A times the acceleration of A times time is equal to the negative mass of B times the acceleration of B times this change in time. And what is acceleration times time? Velocity? Close.
Displacement? No?
Farther away.
Velocity, I'm saying.
Change in velocity?
Yes. The change is important here. Yeah, it's change in velocity. So I have mass of A times the change in velocity of A is equal to negative mass of B times the change. Wow, it's getting worse and worse. Change in velocity of B. And when you're finding change, math-wise, what are you doing?
Subtracting final minus initial.
Okay. So I have the mass of A times V A final minus mass of B times V B final. Try that one again. Mass of A times V A final minus V A initial is equal to mass of negative mass of B times V B final minus V B initial. Now I'm going to distribute, and this will be the most tedious line to write. So we have mass of A, V, A final, minus mass of A, V, A initial, is equal to negative mass of B, V, B final, plus mass of B, V, V initial. And that's when physicists get tired. So they decided at this point, MV shows up 4 times, so let's go ahead and come up with another letter to represent that. So why don't we just let P equal MV? So this is just PA final minus PA initial is equal to negative PB final plus PB initial. A dramatic pause here, in case there are questions. All right, so I got this, whatever P is, I've got this value of P for A final and initial, B final and initial. Let's get all the initials on one side and all the finals on the other. So I'm gonna bring PAI over to the right and PBF over to the left. So I end up with PA final plus PB final equals PA initial plus PB initial. And this makes physicists' hearts go all a-twitter. Because whatever this value of P is, my total final is equal to my total initial. And what do we call that in physics?
Wait, what did you say?
Like that whatever this value of P is, besides MV, that my total final value is equal to my total initial value.
Which conservation of energy?
Or just conservation. It's conservation of P. And so now we should probably come up with a name for P other than just calling it P. And that's momentum.
So is P like the official thing for momentum?
We can define it.
Okay. So momentum is equal to mass times velocity.
Yep. Unlike with conservation of energy, our vectors are still involved at the end, so we do not lose information about the direction. So the positive side, the plus side to using conservation of momentum is that we don't lose direction. The disadvantage is that we still have to handle direction, which is the flip of the pluses and minuses of energy. Just some notational things. This is momentum of individual object. Momentum of group. Now, this is not a hard and fast rule, especially since capital P's and lowercase p's look a whole lot alike. But in textbooks, typically they'll use a capital B when they're talking about the total initial momentum or total final momentum, and lowercase p when they're talking about the individual ones. I will flip back and forth. I tend to use lowercase consistently, but occasionally I might throw in a larger capital P. And I think P is used because of René Descartes. I'm not quite, I cannot. I saw one place which talked about why they used the letter P, but I forget what that was. And I've seen more than one video where they say, why do they use the letter P for momentum? I don't know, so,
They felt like it.
yeah, in my case, it's because I don't actually remember. Now I want to introduce one other terminology here. This force times time is known as impulse. And that's usually when I introduce my most obscure clue. Perfume commercial from the 70s. When someone suddenly buys you flowers, that's called impulse. Now, if we follow the trail down, I don't flip sides. I don't move anything across an equal sign until I get to here. This is the last point before I start moving stuff across the equal sign. And so my impulse there is also equal to the PA final minus PA initial, which is just the change in momentum of A. So my impulse is equal to force times time, which is also equal to the change in momentum. So if you're ever asked about the impulse of impulse that is imparted on an object, whichever one you want to solve, based on what you're given. I also want to point out one other thing here, is that if we look at this part right here, if I divide by time, I get that force is equal to the change in momentum over the change in time. And if you think about that, if that's the case, that's the change in mass times velocity over the change in time, which for everything we have done up till now would be the same as mass times the change in velocity over the change in time, which is mass times acceleration. However, this step to here is not always the case. Sometimes the mass changes. And so this actually is the more generalized form of Newton's second law, because it does allow you to account for the change in mass.
The delta mass times velocity over change in time.
So what this would actually end up being if mass changes would be mass times change in velocity over change in time plus velocity times change in mass over change in time. If you had calculus, it would seem natural that you'd use the product rule. If you haven't had calculus, then trust me. Amy, you look like you're struggling to see. Is it a glasses thing or a color thing? Okay.
Then that's fine, I'm just taking pictures of it and then zooming in.
Okay. If you want to swap, you let me know. That's no problem.
I've had some students have difficulty seeing certain colors, so didn't know if that was an issue.
Amy has difficulty seeing all of them right now.
I did have a student sit right there before, so we can move you closer if you like.
I'm gonna try to way too close then. I'll just blur out the pictures with my phone and zooming in.
All right, any questions before I continue our racing? Poison.
So, so you said that impulse is equal to force times, is that change in time?
Yeah, or time.
Okay, and that's also equal to, change in P, and that's, momentum?
Yes.
Okay. So then why did you put that force is equal to change in, like, take me from, like that arrow, basically those two.
All right, so Impulse traditionally is defined as just the force times time. If force is constant. If force is not constant, you're doing an antiderivative or an integral. But force times time. If we continue looking at the left side of the derivation here, we eventually got to this point right here. This is just it's a final value minus initial value, which is change. This is the change in the momentum of A. So it's making the claim that force times time is the same as the change in momentum.
Okay.
So since impulse is equal to force times time, which is equal to the change in momentum, I then looked at just these two, they're equal to each other. And if I divide by time, bring that over to the right-hand side, I have force as change in momentum divided by change in time, which gets me here. Do you want me to keep going?
Oh, no.
Okay.
If I was just, wondering about that first part, and you explain it well.
Okay.
So, I guess piggybacking off of that, if you're saying that if mass is not the same, then our momentum would change. What, from where we have change in mass times velocity, you've got an arrow that goes up. Yes, what was that, talking about?
So up till now, we haven't had any objects really changing mass.
Yeah,
So therefore, in those cases, if mass is a constant, it would factor out, and this is the path you take, and we get to where we've been.
okay,
However, if mass does change, like rocket problems are usually the classic ones, because you're burning fuel, shooting fuel out the back.
yeah,
If in those cases where the mass does change, this is really a more generalized form of Newton's second law.
okay. It's just the product rule with
Yes,
mass and velocity, okay.
absolutely. So if a rocket shoots out 500 kilograms per second, or burns out 500 kilograms per second, that would be change in mass over change in time.
Okay.
What would if you're having a change in mass, what would your first M be then?
So typically when you're doing this, using the chain rule, you're dealing with instantaneous change.
Okay,
And so that would be the mass at that instant.
gotcha.
Yeah, there's difficulty with applying that without calculus. So we're not gonna do much with that. I typically don't do the rocket problems. However, I just wanted to at least introduce you to what that opens up.
I apologize if this is kind of a basic concept that I'm missing, but when you have the change in something, is that always a positive number?
No.
It depends on the direction it's moving in. So if you're losing mass, the change in mass would be a negative number.
Correct.
Okay.
So I guess in the case of the rocket, if you're burning 500 kilograms per second, that change in mass would be negative 500.
Okay.
I was thinking of like a rock falling down a cliff. Flaking pieces, you know?
Oh, breaking up as it goes?
Yeah,
We would treat that actually a little bit differently because the change in mass per change in time is sort of instantaneous.
oh.
And so
okay.
we would treat that as an object splitting up into two objects as opposed to burning off.
Okay,
And it'll be a momentum problem.
Gotcha.
We'll get to it. Any other questions? So let's just start out with a simple example. And then typically with physics, you start out with the simple examples and most people go, okay, I get that. And then suddenly, even though it's just the next step, suddenly at some point along the line, there's gonna be this huge gap in your head and you're gonna go, wait a second, shouldn't there be an intermediate step? Probably not, because that's the way physics is. It works really well to a certain point and then suddenly there's a leap. All right, so let's start out with a one-dimensional problem, so a 1D collision. 5 kilogram mass going at 2 meters per second. A 3 kilogram mass going at 4 meters per second. So this is before. We'll worry about what happens when they collide in just a second. So let's just start out with, what is the momentum? And I'm gonna put a little subscript 5 here to indicate the 5 kilogram mass. What is the momentum of the 5 kilogram mass at this point, before the collision?
Are we assuming this is the positive direction?
If you wish.
Okay.
That one.
Was that an okay that you wish it?
Yeah.
Okay.
It's 10 for mass 1.
What are the units?
Newtons?
Nope. Not if you're stopping there.
Meters times kilograms per second.
Yep. Kilogram meters per second.
And this-
Now, the reason I said it's not newtons if you stop there, if we think over here, the units have to match. The units of impulse have to match the units of force times time, which has to match the units of mass times velocity.
Okay.
Units of mass times velocity right there, or it could also be a Newton second.
Okay.
There is not a one-word unit for momentum, which gives us a little freedom here. You are allowed to make up a unit if you wish, but there's some ground rules. First Brooke.
Is this just the momentum of the left box here?
Yes.
Okay.
If you wish to make up your own unit, and some students do and some students don't, depends on how much you want to write. It cannot be you cannot use any symbol that's already being used. You can't use a capital N and say, all right, we're going to use capital N to stand for the unit of momentum. No. So capital D is not being used for any unit that I know of, at least not in this course. And so I'm going to define D as a kilogram meter per second. At this point, because I've written that now, I can now say that this is equal to 10, and it's honoring Rene Descartes. 10 Descartes.